Yeah. First of all, I would like to thank the tie-up of this program, Typing Institutes, both the RGNYID and NITJ for organizing this wonderful program. And also, I would like to thank Professor Lalita Avasthi and Director NITJ and Director Sir of RGNYID and David G and other people who actually involved in this program, and they thought of me and inviting me to this session for delivering a talk. And I would also like to congratulate and thank the participants for joining this event during this pandemic time, and I appreciate that they appreciate their learning instinct, and it's good that some activity is still going on even during the pandemic time, and we are having some teaching learning process going on. So in the era of computational intelligence and artificial intelligence and data science, and we are talking about huge amounts of data, big data, and this big data needs to be stored at some place, and we should have efficient mechanisms to process this data. And probably we need more number of processing units, computational units, storage unit, huge amounts of memory. Like a lot of resources are required in order to implement or execute these applications or this data. So cloud is one of the biggest tool for processing the data and storing the data, and that's why we are talking about cloud computing in general. And there are a lot of innovations happening day by day in the cloud. A lot of architectural changes are coming up day by day, and this course is very important in that context in the current era of technologies, where cloud has become an important tool for data scientists as well as application developers, and even the IoT like devices actually are having poor resources. So having poor resources is one of the difficulty thing, and where they cannot run the applications, they cannot store the data, they cannot and even if they run the applications, if they are wireless IoT environments, probably there will be resource constraintness in terms of battery power, energy saving, and all that. So one of the fix to IoT kind of applications is to use cloud as a backend, where you run the applications in the cloud, you store the data in the cloud, and use your IoT device as sensors collect the data, forward the data to the cloud, process it, and get the results back to the IoT systems, and transfer it to the customer or the user. Social media applications are also growing like anything, and people are addicted to social media, and huge amounts of data is increasing because of the social media, particularly your WhatsApp, Twitter, your Instagram, Facebook. These are all different sort of social media which you are using for managing with your social media data. The other side, we are also having several streaming applications and gaming applications, which actually require huge amounts of storage one side, the other side computational power. For example, your streaming applications or your OTT platforms like your what is called Prime or Hotstar or any other platform you take, right? These platforms are actually like using cloud as a backend, and they are storing your videos on the cloud, and they are processing the videos for faster delivery and efficient delivery. In order to the streaming should become more efficient and qualitative. At the same time, security is maintained. Okay, and your gaming applications require huge amount of processing capacity because most of these gaming applications are visual based or image based, and doing a lot of image processing in the backend, and with a lot of what do you call speed, accuracy, because gaming requires speed and accuracy. And these applications typically cannot be run on mobile devices straight away, or your you need high-end systems at the client side. So these high-end systems cannot be provided at the client side. So one of the fix can be that your application is run in the cloud. So your cloud is having highest number of resources, the computational power, the storage, the memory, and all that. Where you run the applications in the cloud, and from the gaming application, you send the input parameters to the cloud, and the cloud actually performs the gaming operations, and the output it shows on your screen. So this way you can speed up the activity and provide the qualitative services to the customers. So there are multiple similar applications which require cloud computing as a backbone, and in terms of storage and processing at least. And otherwise, in many other forms, we will discuss in the coming time. So what I'm trying to say is like cloud is one of the important concept that someone has to learn, being the computer science or similar background personalities. And I mean, and you must try to take the advantage of these features of the cloud for developing your future applications and future technologies. So let's quickly understand why cloud. So in the olden days, we used it to run huge, highly computational applications, typically on the clusters. And over the period of time, the clusters started exhausting to compute the applications. So people started using supercomputers, and even the supercomputers were insufficient to run the applications. So at that time, people started to using a grid of computers where it's not only my computer system, but some of my friends' computer system. So here I must introduce one important terminology, that these are the clusters and supercomputers are high-end, highly costly, expensive computing systems, and only specialized universities or organizations or industries use it to procure them, and normal people who wanted to perform certain computational intensive applications, it is very difficult for them to procure these resources. So slowly there is a technological shift, and people started why should I depend on these high-end and expensive systems like clusters and supercomputers? Why don't I make use of easily available commodity computers where they are cheaper and easily available? So the grid, what I'm trying to say is here, grid computing is one of the popular technological shift where your clusters and supercomputers were expensive, and people wanted to have cheaper computers to perform the same tasks that I am performing with high-end computing systems like clusters and supercomputers. So grids is grids are the commodity computers which are cheaply available in the market. So I'll give you a typical example to make it simple and quick to understand. Let's suppose that there is one of your friends who is sitting in US, and it is your desktop computer system. You want to, the important point is that so you have one friend in your US and you are in India. You both wanted to have more computing systems. Like you are having one system, your friend is having one system. Let us say. So in your daytime is a night time for your friend, and your friend's daytime is a night time for you. So one possible arrangement you both can have is like during your daytime, you use your friend's system. So it is a night time for your friend. So your friend's system can be used by you. So that way you are using two systems instead of one system, and your night becomes a day for your friend, and your friend can use your system. So that way your friend can use two systems again. So I mean, this is the arrangement where normal desktop systems can combine on a collaboration manner, on a sharing manner. They can have multiple computing systems together to perform the same task, same application. So that is the motive of sharing of computing resources in the grid computing, where their focus was to run the applications. So these are all different sort of distributed computing systems, because there are several computing systems distributed across the globe now. Someone in your friend is in US, and someone is in other place, and someone is in other place, something like that. So you can take multiple friends together, collaborate, and perform your application execution. Okay, I mean, this is the beauty of computational, technological achievement, where with simple desktop-like systems or low computational capacity systems, cheaper systems, when they are collaborating in multiple numbers together, they can perform like your high-end systems like supercomputers or clusters. So typically these supercomputers and clusters were homogeneous systems, but from the grid computing onwards, the strategy changed and they started incorporating even heterogeneous computing systems to perform the same set of tasks, same set of applications. So this started the new technological introduction to your application executions in a distributed manner with simple commodity computing systems, cheaper commodity computing systems together in a collaborative manner, or more better word is in a sharing manner. Okay, so people started to share the resources to run their applications. Of late, people adopted this new ideology, and they started, why don't I take the advantage of this sharing business, and instead of suppose I'm the person who is sharing my resource to my friend, one of the fix can be that why only to a single friend? Why not to the people who are in need across the globe? I'll share my system during my free time, not only during the busy hours at which my friend is using. Some other times my friend may not be using it, and my system is maybe still free. So that way I can improve the utilization of my computing system, right? So instead of only with my friend, I'll share this system with all the people who are in the need across the globe. And what I will do is I'll make this system shareable to my friend as well as all the people who are in need. So that means the same system now can be usable by my friend and many of the other users, during my off time. Okay. So this way, now it has become service oriented, where I am giving my system as a service to many people who are in the need whenever my system is available. Okay. So the ideology now changed. Instead of just running a specific application in which people are collaborating and running the applications in a grid of computers, now the same grid of computers, same set of computers together are provided as a service to the other people who are in need, apart from running my applications. So this way, now all this group of computers are part of now services to other people who are in need. And this service computing strategy started with sharing, what I mean to say, sharing of these resources started with your cloud, and that's how cloud has become so popular, and the resources are pooled together, like not only my system but all my friends systems and all other systems together are pooled as one set, and from the set, whoever is in need will take the resources and they may take the advantage of these resources to run their applications. And instead of one application, because earlier the goal of these grids and clusters and supercomputers was to run a single application. By the time cloud has come, now from the pool you take any resource and you run any application from anywhere, from any time, from any device. That's the goal of this sharing. So that's how cloud has become so popular, and people started adopting this new and innovative change in the technology. So that's a major technological shift in your computer science, and that's how cloud has become very, very popular in the industry. Okay, and the other side, there was other important reason was that people started thinking about IT agility, where like when I'm like running some business, like suppose I'm a teacher, I'm from educational institution, and why I should worry about installing the computer software, installing the applications, installing the buying the hardware. Let this be provided by somebody else, so that I can focus on my education, I can focus on my studies, and I can focus on my teaching. Okay, so this way I can get the advantage of focusing on my work rather than depending on what you call IT infrastructure development and all that. So let this IT infrastructure development be dealt by somebody else who is expert in that area. And the other side, we have important achievement because of this adoption of cloud is that when we see the expenses, we see that like 70% of the expenses are going for maintenance. That means if I am installing my servers, I am installing my tools, softwares, and all that, then in order to maintain that infrastructure and all that, I need to spend 70% of the budget myself. Instead, let this investment be done by somebody else, and who provide the resources to me, so that all this budget is shared by the people who are using the resources. So that's how my budget is typically reduced. Okay, so the total investment substantially reduces if I share this budget with many other people who are sharing the resources. So that's another important concern. And of course, third important concern is that the financial expenses are drastically reduced. I mean, cost is reduced because all this budget is shared, and the resources are not at my venue, so somebody else is managing. So I don't need to have any maintenance engineers and humans and all that. And next important concern is the space required, the real estate, what do you call, the business management, the infrastructure management, and other costs involved, like even cooling facilities. I need to take care of cooling facilities, and all this infrastructure is very much reduced because of the adoption of cloud. So these are the major advantages of why we should go for cloud computing environment. So next important concern is what makes the cloud computing possible. How this sharing is really possible. When we are talking about sharing, we said that the same set of resources are shared by multiple people. But how this is really possible? So when we see the infrastructure, any infrastructure, then we see that there is a hardware in the infrastructure, and above the hardware there is an operating system running, And on the operating system, we have a set of libraries or compilers or libraries or whatever it is required. Libraries are installed, and over the libraries, you are actually running the applications. So here, in this stack, software stack or hardware stack, the infrastructure stack we call it as. So in this infrastructure stack, we have several layers where, interestingly, we can have we can create a shareable environments where like there are some privileged instructions restrict the access from access to the hardware resources from your operating system. Okay. Or else, if you are using general instructions, then there is a pipeline possible, from your applications directly can access the hardware, or your libraries can directly access the hardware, or your operating system can access the hardware. I mean, that means like if you want to run an application, then probably it needs permission from library, but library needs permission from operating system. Operating system needs permission from hardware. Like this is how the stack works. But some other times we can also have direct access to the hardware based on different sort of applications. So we have different types of interfaces accordingly, like either like assembly instructions or system calls or API calls, or different sort of sources we have through which we can access to the resources what we have on a computing system. Okay. So accordingly, we have several layers of virtualization, where a layer of virtualization actually helps in what do you call adapting multiple computing system to be shared. Okay. So there are like emulation-based virtualizations, operating system-based virtualizations, or even you can have application-level virtualizations. For example, Java Virtual Machine (JVM) is one of the popular application-level virtual machines we have. Or VMware applications are OS-level virtualizations, right? And like Bosch are you can say are emulation-based virtualizations. There are different sort of virtualizations that can be adapted to your computing systems, where the resources can be accessed from different layers and different levels of computing systems. So operating system virtualization, where you have like on your hardware, you can have a host operating system. On that, you can have virtualization layer, and you can have many guest operating systems, or you can say virtual machines. These are the virtual machines. So on which you run your applications. So your application will take the permission of guest operating system, will take the permission of virtual layer, and then host operating system, then hardware resources. That's how it works. But the advantage is that on the same environment, I can have three different people working at the same time. Suppose in this given figure, there are three guest operating systems. So that means that I can run three different customers can work on this system. So that means same hardware resources are shared by three people. Okay. And this is called type 2 virtualization. And there are several virtualization tools we have, like typically the VMware player, very popularly used one. Otherwise, virtual PC is another popular tool we have available in the market. But some people will also use Linux and other areas, KMO as the virtualization tool. But these are all very popular virtualization tools for running your, creating the shareable environments on a particular infrastructure, given infrastructure. On contrary to that, there is no host operating system here. Directly hypervisor software is installed on your hardware. The virtualization software is called hypervisor software. It can also be installed on directly hardware, and then we can have multiple operating systems installed on it. So in this way, we can minimize the usage of extra layer of another operating system here. So these are usually adapted. These kind of environments are usually server level systems, and ESX servers. VMware ESX server is very popular tool, like most of the servers use for developing virtualization, creating the virtualized environments. So we have multiple virtualization environments that help in creating or a facility to share the resources of the infrastructure. Here, the infrastructure is your hardware tools in this particular case, and you could do this similar kind of environment for your software and data or whatever you call it. In this specific hardware virtualization, we call this as type 1 virtualization. And we could also have like a modified environment where there is a host operating system in between your virtual hypervisor and hardware, but you have guest operating systems or operating systems, whatever you call it. But they can be modified in such a way that they can bypass the host operating system and they can directly get into the hardware resources straight away. And this kind of environment, what you call it as para-virtualization, it is somewhere between your type 1 and type 2. And Zen and VMware are having, Zen is having para-virtualization activated, but nowadays almost all the tools are having para-virtualization implemented. Now there is separation of like several tools here. Yeah, as I mentioned a couple of minutes back, if I use the cloud computing, which actually uses the virtualization as the backbone for its implementation, where it is sharing the same set of hardware resources by multiple people. That's why instead of one machine, like instead of having 3 machines, now one machine I'm creating, or I'm virtually creating it as if like there are 3 machines available. So that in order to like provide 3 people, instead of creating 3 machines, now I'm creating 1 machine virtually available for 3 people. Okay. So this way, number of machines required are drastically reduced. So this is what we are trying to show in the slide here. So the servers earlier, without virtualization, we used to have like 1,000 servers. Now I can manage the same result, same effort with just 80 servers. So this is the drastic decrease in the cost for me, and the space requirement, and many ways it is a very, very big leap in the savings to me. So you can see here switches required are reduced, the space required is reduced, the power requirements and cooling requirements are also reduced. Overall, the costs are drastically cutted or saved because of this particular virtualized cloud computing environments are adapted. So that's the beauty of cloud computing, where it virtually provides the same resource to multiple people to run the different applications. And some people may say that how this is beneficial. Like if I use the same system for multiple users, would it not lead to reduction on the performance? Yeah, it will partially reduce the performance, but the important point here to indicate is that if you try to check with your computational resources. For example, you take just the CPU in your computing system, in your laptop or desktop or whatever it is. It hardly is busy for only 15% of the time. Rest 85% of the times it is underutilized. It's not at all used. Okay, that means the CPU, it can't be tired. It can't be it can be given 100% utilization, but unfortunately the resource is underutilized. Suppose if I create this CPU virtually into 3 slots, then I'm giving this 15% to one user, another 15% to the other user, another 15% to the other user. That way, now the CPU has become busy for 45% to 50% of the time. That means the CPU utilization we are increasing here. We are not reducing the performance, but we are utilizing increasing the utilization here by creating the sharing environment for the CPU. In the similar way for memory, in the similar way for the storage and other resources. So this way, the same resource utilization we are increasing, but because of the virtualization, we are adding one extra layer in the environment. So because of that virtualization layer, there would be slightly reduction in the performance, but that is very, very negligible, like, in the performance reduction when compared to the advantages what I am getting because of, like, virtualizing and creating as a shared pool for multiple users. So that's the beauty of cloud computing, where it improves the performance. In fact, it improves the utilization of the resources and gives more advantages than what really is possible with the single user systems. So that's why cloud is very, very important. Yeah. To sum up, the server provisioning time is reduced from 46 days to average 46 days to average 35 minutes. Like suppose in my institution, if I have to buy a server, then probably I used it to take 45 days time. But now just with a couple of mouse clicks, I can get a virtual computing system or virtual server, and I can use it, and I can, whenever I want, I can use it and I can revert it back. And server costs are reduced by 40%, deployment time is reduced by 40%, and as I mentioned, the utilization, this is the most important part of the whole story, is that the utilization, as I mentioned, was having 10 to 15% of utilization earlier, has drastically increased it to 40% to 50%, which is very, very important as far as any computing resource utilization is concerned. Okay, so now let us formally understand what is actually a cloud computing is. So to formally define what is a cloud computing, just to hint you that it is a shared pool of computing resources. So that's what we are talking about from a couple of minutes, that it is the computing resources like your hardware, your software, including your networking resources, servers, storage, applications, and including the services themselves can be pooled up together as one set of resource. Okay, and these resources should be in such a way that you have a flexibility to configure them according to your convenience. So you provide a set of resources at single point, and in that set of resources, you design these resources in such a way that you can configure according to your convenience. Okay. And not only that, but these resources, providing the resources is not sufficient, but they must be made available in a comfortable fashion. So it also enables you to ubiquitously, conveniently access these resources, in a sense that anywhere you must be able to access it, anytime you must be able to access it, and from any device you must be able to access it. So that's the flexibility it should be providing with minimal management efforts. And the provisioning speed must be so fast that it shouldn't take too much time for provisioning or releasing of the resources. So the important point here is that once you use these resources, after usage, you must release these resources so that these resources can be used by somebody else, like my friend or whoever it is, who wants to share these resources. That way, multiple people can share the same set of resources for efficient utilization of these resources, as well as efficiently performing their required tasks. So how this really happens? So there are 4 important pillars that actually make the cloud computing applications to run or possible, are the service-oriented architecture, the virtualization, the autonomic computing, which is actually makes you minimal effort. Everything should run automatically, and most importantly, the utility computing, where it allows you to share the resources and meter the resources, so that whatever the period for which you are using these resources, if they are on payment basis, then this metering will help me in billing the costs according to the period of usage. So typically cloud is provided in multiple ways. Usually the private cloud is having limitation in terms of access rights, where only a particular organization or particular set of employees are having access to this cloud. Public cloud is having access to all the people who are in need. So it is having all the resources, and public, anyone across the globe can make a request for the resources, and they'll get the services based on the billing cycle what they have. And we could have combinations of all this. And apart from that, there is a concern called how you provide these cloud services to the people. Okay, and the provisioning of these cloud services, what you call it as delivery model, is there are different sort of delivery models we have, where only infrastructure needs can be served by infrastructure as a service, where your hardware components like networks, servers, whatever we discussed a couple of minutes back, can be provided as service. Or any development platforms can be provided as service, and any software can be provided as service. And in fact, if you see the list, even like security, desktop, function, analytics, sensors, whatever it comes to your mind related to computational science, that can be provided as service. That's why it is called as everything as a service, and we notate it as X for everything or anything, and XaaS as a service. So that's how cloud can be provided as a service. So this is a typical cloud environment what we have in our HPC lab. Okay, where just to show you that these are now your servers in the virtual form. What you need to do is you just need to click on a particular line and create a virtual environment and install your software on this, and make use of this virtual computer to run your application on the servers in my HPC lab. So that means I'm providing this web interface for you, and using this web interface from your home, we can access this cloud services. Click on one of the link, then you get the virtual machine to you, and you run your application on this virtual machine, which is available. Actually, this virtual machine is available in my HPC lab. Okay, so in the similar fashion, Amazon Cloud, for example, or Google Cloud, or Microsoft Cloud, or you think of any other cloud, for example, WhatsApp Cloud, Hotstar Cloud, they are having their own data centers, like my data center in HPC lab. Okay, you can have different service providers who actually have the data centers in which they have these virtual environments. And what you need to do is from your desktop system, from your laptop or tab or mobile device, you log into this particular environment, and through couple of mouse clicks, select a particular instance of a virtual machine, because as I said, on a hardware interface we can have multiple virtual machines which are running different guest operating systems. So each one is called as one instance. So one customer can have multiple instances possible, right? So you click on this and create your instance, one virtual instance, and on that you install your software. That means you configure your virtual environment according to your convenience, and you run your application, you run your services on it. So that much easy it is for anyone to access the cloud services. So they act very similar to the computing server which is available in your local lab or local data center. So you are not managing the local lab or data center. Instead, in my HPC lab, I am managing, or in Amazon data center, AWS is managing, or Google is managing. So other people are managing, and you are just with the clicks of mouse, you are accessing those systems from your desktop system remotely. So this is how, with the remote access, you can get into the server's access. That's the beauty of your cloud computing, where you can see everything, not only the hardware, servers, but you can think of all the sort of instances like storage and other things. Like if you go through any website, like for example, you open a AWS website and you try to see, they will provide a lot of cloud services in their listing. So cloud computing actually is good one side, but the other side, it raises like a lot of new challenges and issues, and here where the research evolves. So particularly the virtualization is evolving like anything, and people are started to redesign this virtualization to make it more efficient, because virtualization is the key source of cloud service provisioning, and there are a lot of innovations coming up. And one sort of improvisation or innovation in the virtualization is adoption of containers, and even containers are further optimized, to better deliver the services with the help of the tools like Dockers and Kubernetes. The other side, we might need one cloud. I have like multiple clouds, let us say, and there is every possibility that one might need the same cloud. May not be possible to be used by a single user. Some other times multiple clouds may be used, and one cloud resources may be required, services may be required to be transported or ported to another cloud. So for example, you have a Gmail account, and all your emails you wanted to move from Gmail to, let us say, Microsoft account, or let's say you want to move all your emails, Gmail emails to, let's talk about any other email service provider, then typically it's not possible or easy. Okay. So this kind of business, what you call it as vendor lock-in, or the problem of interoperability. That means I cannot run the same services on different sort of cloud service provisionings. So we need to redesign the cloud in such a way that these vendor lock-in problems and interoperability problems need to be addressed. The other side, we also need to talk about migration issues where some people who are not using cloud, they wanted to move to or migrate to cloud. Then this in-house system to cloud migration is one problem, and some people who wanted to move from one cloud to the other cloud. So this migration from one cloud to the other cloud is another problem. So these migration issues also need to be addressed in your cloud computing environment. And apart from that, the billing issues, metering issues, and agreement issues, several issues will be there, and we need to think about that. But the other side, service provisioning side, the provider should provide the resources in more efficient manner, where the utilization of the resources increases, and more efficient scheduling techniques they adopt, and provisioning techniques they adopt. So these are the three key areas of cloud where a lot of research is going on, because every day new techniques are coming up to improvise the quality of service provisioning for both the sender side as well as to the receiver side. And of course, we have to do all this with the fairness and optimization adapted, along with ease of access provisioning and the quality of services provisioning. Okay, so these are all important in terms of provisioning side. The other side, these are important in terms of provisioning, sharing, and efficient delivery of the services. So one of the other services what we talk of is the storage and file systems management, where we can adapt the new technologies like MapReduce, apart from serialization what we have in the olden environments. And alongside, we have to think about going green, where the design of all the mechanisms, starting from virtualization to parallelization, we have to adapt everywhere energy, power saving techniques, energy management techniques, so that the cloud doesn't consume a lot of energy in the delivery of the services. So apart from storage, we also need to talk about the processing, where we should be able to run high performance computing applications. And these are the two important things. Like typically the applications are categorized as two ways: data intensive applications where storage is more important and processing of the data is very important, and the other side, compute intensive applications where the processing is more important. So high performance computing applications are computing intensive applications, and data intensive applications are connected with storage, file systems, and MapReduce management systems. And in every stage of implementation, you must consider security, privacy, and trust as necessity parameter in the delivery of it. And along this side, we are having a lot of new trends of implementations coming up, particularly, for example, adoption of artificial intelligence, that blockchain kind of technologies is one important area where you need to redesign, rethink about all these architectural achievements in your technological achievements in your cloud environment. And apart from that, new kind of applications are evolving, like for example IoT, which necessitates you to redesign your cloud computing environments, where a new kind of cloud or cloud businesses are evolving, named with edge computing and fog computing. If time permits, we will discuss about these also. So I mean, that's the basic idea of what is cloud and all. So till now, if you have any questions, I'll take just 2 minutes time for taking the questions. Then we will go to the next part of it. So now you can unmute yourself and ask the questions. Okay, good. So I believe like participants are not sleeping, and
there is one question, sir. Sir, is any backup is maintained for cloud data?
Yeah. I mean, so typically cloud is implemented in like in this fashion, where like you have a cloud, and this cloud may be made up of multiple data centers. Okay, let's call this cloud. So this cloud may be having a single data center or maybe multiple data centers. Let's call it as DC data center, and could have many data centers in fact. Okay, and these data centers need not be at the same geographical region, but they can be situated at different geographical regions. For example, this data center is in, let's say, in India, and there may be some other data center which may be in US, and some other data center may be in other country, like maybe UK or something like that, different countries. So these cloud is a combination of multiple data centers having like their computing systems separated at different geographical regions, and in each data center we will have like hundreds of thousands of computing systems, which you call them as hosts, and we can have multiple hosts in each data center. Okay, like hundreds of thousands of hosts, and on each host, like on each computing system, we will have multiple virtual machines. Okay, so this is one virtual machine we are talking about because of your virtual environment. So that means when I am storing or performing some application, let's say this is my storage, right? And for this storage, let me call this storage as D1, data D1. So this data D1 typically is replicated in cloud. The cloud is actually, it's a management tool. Okay, what it is doing is, like, it is managing these virtual machines, it is managing these hosts, it is managing all the hosts in the data center, it is managing all such data centers together, as if like it appears to the customer, whoever is interested to take the services of this cloud, as a single system. Okay, what you call it as single system image. Typically, in the short form, we call it as SSI. Okay, so like as I've shown you in the previous figure, like this figure, it is the single browser through which you are accessing it from your laptop system, but you don't know whether you are accessing this system from the India server or data center or UK data center or US data center. Where it is, you don't know. And among these data centers in this cloud, as I said, like you have DC1, DC2, DC3, and so on, right? At different geographical regions, and in like this is in India, this is in UK, as I mentioned. Let's say US, let us say. Okay, so whatever the data I have, like whatever the data I'm storing in this virtual machine, let us say this is the data, right? Its copy is made usually in multiple data centers. Typically, three copies are made. Okay, three copies of made of each data. So that way, even if one data center collapses due to any reason, fails due to any reason, the same data is available in two different data centers as a backup. That's the first important point. Second important point is that, I mean, they are not from the same data center or same geographical region. So the chances of failure in the second geographical region are pretty much low compared to this first geographical region. So even like due to earthquake or for any reason, the entire data center is collapsed. Still, like there is a backup of all this in two different places at two different like countries. I can say, like, so let's say this is US based data center which collapsed. Probably you may be having you have a data center in India, you may have another data center in UK. So like in which the same data center data item D1 is kept. So even failure of one data center will can be retrieved back having the backup copy to the other data centers. That's the beauty of your cloud. Yeah, that's a good question you have asked. Yeah, any other questions you have? Okay, so moving forward. So let's try to understand what are the typical trends that are there. And
so before that, there's one more question.
Yes,
in
sir.
what way cloud is used to store biological information?
It's not about like one application. Biological information is one application, but like as I said, it could be done for any other application, like social media application or your streaming application or gaming application. Biological applications are one application. Like for example, your genomics data, bioinformatics data, whatever you call it, like any data, damn data that is converted into, I mean, that is in the digital form. That's important point. Like if it is in the digital form, can be stored in the cloud. Okay, as I mentioned, there could be multiple clouds the customers may be talking to. Like for example, a single customer may be taking the services of Dropbox, Google, or Gmail. Maybe Microsoft, or like from multiple clouds, right? Is possible. Alternatively, a customer may be taking the services from one cloud, but this cloud may be having the connection to other several clouds, and it may be taking the resources from different other sort of services. That means one cloud may be taking the services from other cloud. So this is called federated cloud or kind of hybrid cloud, where actually you are connected to one cloud, but essentially this the services or the resources what you are getting need not be from the same cloud. Probably it may be from other clouds also, right? And as I mentioned, some other times the services what you are getting from one cloud may need to transported or ported to some other cloud, or migrated to some other cloud. Okay, and this way these two clouds must have some sort of interoperability, and these three clouds must have some sort of interoperability, or in the federated cloud environment or migrated environment or cross cloud environments, or multi-cloud environments, like in any cloud environment, any sort of cloud environment, one of the biggest challenges is to have the interoperability and efficient service provisioning. So you need to redesign the cloud architectures and business models in such a way that all sort of these kind of internal architecture designs need to be taken care such that the cloud becomes meaningful and feasible. Yeah, as I mentioned, other important innovation in the cloud implementations is adoption of the containers. So in the olden days, people used to have the virtual machines where the virtual machine is used to have, as I mentioned, the hardware, and on the hardware you used to have your operating system, and on the operating system you have virtualization software, what you call the virtualization layer, and where you can have multiple like virtual machines, or you can call them as guest operating system. Like it is having multiple layers of implementation. So these multiple layers of implementation complicates the execution of the applications and implementation of the software, tools, whatever you are talking about. So alongside of virtualization environments, there is a innovative study took place. In fact, it started in way back in 1970s from IBM, and but at that time the goal of this virtual environment or virtualized virtual machines was to manage the what is called mainframe computer systems, where people used to access the computing systems through the terminals. They used not to have a separate computing system for the individual users. At that time, they wanted to have the same single machine virtually available through the terminals for the people. So that with that motive, the virtualization concept started, and virtual machines were introduced. And at that time itself, the concept of containers initiated. Okay, along the virtual machines implementation parallelly, and they used or they adapted the internal features of the Linux. Linux is having wonderful set of features, which actually you can use these features in such a way that two important features, I will just list them in a couple of minutes. Two important features, what you called as namespaces and C groups, are two important features that actually virtualize the hardware components, or you can say isolate the what. It's not, I mean, virtualization is not the right word here, but isolate the resources. That means if I have multiple customers using the same machine, same hardware resources, what I can do is, instead of guest operating system, I can avoid this guest operating system. I can avoid this virtualization layer, and I can allow these customers to use the same single operating system, but here the Linux operating system, and they can adapt these hardware resources in isolated manner, so that one user is not interrupting the other user's resources. So this is the beauty of your Linux kernels, where the performance compromise due to your virtualization layer can be reduced, and now the performance can be substantially improved. It is almost like the same on the same hardware, the applications are running on the same operating system. The applications are running, so they appear as if they are running on the bare metal computing systems, the real hardware. Okay, and this way LXC is kind of popular first commercialized Linux container, which of late has been adopted by Docker in efficient manner. people used to have this LXC with what do you call, like, command line prompt based accesses, you can say, where the Docker has made this more visualized and more simplified to provide the container access. That way, it has been like better adapted in the cloud environment. And later, lib container and several other tools were developed, and Kubernetes is a similar kind of tool which does the similar job as Docker container. So Docker is a container, but it is having several, like, it's a kind of ecosystem having a lot of tools within it, and access facilities within it, provisional facilities within it, similar to your cloud service provisioning. So that's how Docker made the containers access very simplified. And you can say this is the first one to, though there are like a lot of development mechanisms in the containers over a period of time, up to LXC, customer, I'm sorry, made it commercially available. But though it is commercially available, but it has become more popular with Dockers and Kubernetes. So the advantage of containers is that you can build the entire application together once and run it anywhere on the system. So you have a container in which you have your the software or application, its databases, its front end, its back end, everything, its tools and everything, and you combine them together. So you combine them together. That's how it is built once and run anywhere mechanism. We can create it, and just you need to configure it to run on a specific machine you want to run with. So that's the beauty of container, which is almost like your virtual machine, where you can just configure it according to your convenience and run it anywhere. And why it is called container? Because it is portable. That means I can, because it is already built on a single box, like a container, so I can run this application. Let's say the website is having an application. Okay, so this application or the website is available, and its database is available, and everything is available. Now what I can do is I can move from one data center to other data center, this entire box of the website, its dependencies, what you call them as dependencies, the front end, DB, queue, all these components are the dependencies of this website. So all these dependencies can be ported on other data center easily. So that way I can move from one computing resource to the other computing resource very easily with the help of containers. Yeah, I've already explained the difference between container and virtual machine. So I'll skip this slide. As I mentioned, containers isolate the environments without you needing any hypervisor. Hypervisor is not there here, and also it is not having any separate guest operating system. Direct host operating system is used by all these applications. And another advantage of containers is that we don't need to have multiple binaries, multiple libraries, separately for each application. Instead, we can have common binaries, common libraries together, on which the application can be run. So this way, the containers minimize the resources required for running the applications and optimize the usage of these resources. Okay, but typically, as I mentioned, these are the features. Namespaces and C groups is the important feature that is required to run your containers, and these are available actually only in Linux-like environments, okay, or Unix Linux-like environments. Typically, the Linux-based environments where namespaces and C groups are available, which are essential components of your containers. Suppose if you want to have the Windows operating system, probably Windows operating system is not having these features. So Windows is now coming up with changes in its architecture to adapt these environments to be cope with container-based environments. So even like these days we can find some of the containerized Windows-based environments also. Okay, the internal concept of containers is that they use namespaces to isolate the processes. Process means an application, and C groups isolates the resources. So now resources are isolated at the hardware level. The resources are isolated for different users, different resource, and at the application level, different applications. The process is application. So these processes are isolated by using the namespaces. This is what exactly we want, to have the separated, same set of resources more efficiently be shared and used by multiple people, but without compromising on the isolation part is concerned. Like there should not be any possibility that one process running on this container should not try to see what the other containers are doing and copy the content, or not even accidentally. So there are different types of what is called namespaces. That means isolation at the file system level, or you can say like host level, domain level, or you can have resource level, you can have process level, you can have network level, or user level. There are different levels of isolations possible, and these are all different sort of beautiful inputs that help in using the containers. Similarly, you can have resources isolation, CPUs, and networks. Several these are all IO, CPU, or you can say networks, or many other things like memory, storage. Everything can be isolated by using different sort of C groups, control groups. C means control groups. Okay. So as I mentioned, containers actually are typically the virtualized environments that can run your applications. But the beauty of Docker is that what they have done is you can create the image of your virtualized environment so that you can actually access this image any way. And they have created a registry where those people who are interested to wanted to have the existing containers, they can just go through the registry. They can for example, client has to create the couple of instructions like build, pull, run kind of instructions. Just with couple of set of instructions, they can pass the instructions to Docker daemon, which is something like a manager, which actually manages the containers and their images, so that people can quite easily instantiate these images. They can run the images, they can build the images, they can run the images, and whenever they want, they can kill the images and so on. So that way, it becomes very easy for users to access the resources. So you can say simply, if I put it in the other way around, so LXC has done the job only up to this level, where it provided an environment how to create the containerized environment. Now, what Docker has done is it adapted the LXC principles in the backend and added extra functionalities to it to create the registry, to create the image repository, to create the provide the user interfaces, access facilities, and many things. That way, Docker helped in making these containerized environments to be accessed by the users very easily from anywhere, anytime. So that's the beauty of it. That's how Dockers have become part of your cloud environment now, and they are almost replacing all your virtual machines with the containerized environments. So nowadays, if you talk with any cloud expert, they speak in terms of containers. They don't speak in terms of virtual machines. Okay, this is a typical example case study of Docker, where you have virtualized environment here. So you can just like with the mouse clicks, you can access the virtualized environments from your Docker environment. So Kubernetes is very similar environment like your Docker, with the exception that this is an open source environment. Docker is a proprietary environment. So you can like make this Kubernetes, since being the open source, you can play with it. You can orchestrate the containers according to your convenience and make it available to your applications and develop whatever multi-container environment according to your needs, and it provides multi-container environments also. So that is a great advantage of having the containers in your cloud environments. Okay, again, I'll take one or two questions quickly for 1 minute. Then I'll take the continuation session for another 5 minutes, 10 minutes, and close it. Okay, next important concern is the microservices. And the other side of cloud, as I told you, virtualization is one important backbone of cloud. And in that, we have seen the evolution from virtual machines to containers, containers to Dockers, Dockers to Kubernetes. How there is a huge evolution, and how they are making the services easier, sharing the resources more efficiently, and making it as a pool and providing it as a service to the users. So this is one side of the coin of your cloud. Okay. And the other side of the coin is the service provisioning. As I mentioned, service-oriented architecture is one of the yet another important backbone of your cloud. And the beauty of service-oriented architecture is that slowly it is also drastically, in fact, not slowly, drastically evolving. Okay. And one of the important innovation in the service provisioning is having the microservices, where instead of having single monolithic application, we can have the application itself can be partitioned in such a way that each partition can be delivered as a service separately. This way, I can more efficiently use the resources and services of the cloud. Okay. So, I mean, let's try to understand how microservices help in innovating the cloud, or evolving the cloud architecture and implementations, and reducing the costs for the users. So these are all typical advantages of the microservices. So I'm not going much details into the advantages and all that in the interest of time. Just I wanted to give you a superficial idea that what a microservice is. And suppose you have, let's say, Twitter application, okay, or any application. Let's take Twitter as an example case study, right? And if you design a Twitter application as a monolithic design, where it is having one user interface and its business logic, and then in the backend database, you have a 3-tier architecture implementation, okay, where the customers are accessing the resources from your user interface, but typically this business model or the business logic and database are actually in the cloud. Okay. So the important concern is that instead of having a single monolithic application, what we can do is the user interface, we can remain it to be a single user interface, and the internal structure can be split into multiple subcomponents, where you have a microservice component of business logic. So the business logic is split now into subcomponents called microservices, and each service is having its own part of the database connected to this service. We can have multiple databases. This way, the services are actually provided through your user interface to customers. The same user interface. What I mean to say, the same user interface to the customers, but internally or inside the cloud, the services whatever we are delivering can be more efficiently delivered by splitting the components. So this is what is the advantage of what you call it as microservice. Let's say, as I told, like Twitter is one example we have considered. So Twitter is having several internal components, or for example, login page, or like registration page, or like posting the messages, or making the friends, right? Several like components there inside it. Okay, every one is like separate tool, you can say. So, but whenever you load the Twitter, it loads all these pages technically, right? So instead of like creating a tightly coupled environment, having all these components loaded along with that user interface, what best we can do is we can separate them in such a way that they can be loosely coupled, and each component can be separated. What is the advantage of this? One advantage is that like I can develop this component on a different operating system, different programming language, and like but they can be just pooled together in my like cloud, and they can be. Another important advantage is that they can be stored on that one side. Development, I can do it on different programming languages. Okay. The second important thing is that I can run it separately. Third important thing is that like I can store or I can run it on separate virtual machine. So earlier I used to run all the components together on a single virtual machine. Now I can run each one on a separate virtual machine. What is a great advantage of it? That means, suppose if I am not using login page, I mean, let's say registration is like one-time job for a single customer. There is no point if a customer is like accessing the login page or posting page, then every time there is no need of like starting the registration page. What you can do is you can make the like virtual machine which is running this registration page can be sleep. I mean, kept in sleeping mode. So that means this can be in shutdown mode. So that way, only the useful services can be active. The services which are not needed at this moment of time can be made inactive or maybe shut down. That's the beauty of microservices, which actually benefits the cloud service users. And why it is a benefit? Because I'm shutting down this virtual machine or I'm making this inactive. So the cost involved to run this virtual machine is now reduced for me. Okay. And the computational resources required to run these entire services is also reduced now. And this resource can be used by many other people. That way, the more sharing can be given. So for the cloud service provider also, it is a benefit for them. So for the user, cost is reduced. For the provider, it has become more beneficial, like profit is increased. That way, we can like more efficiently adapt the services. Okay, so this is a typical example, as I already mentioned. There can be multiple components in the monolithic design. You have to work to all of them together, right? And you need separate virtual machines for running each customer. But for all the customers, it is having all the fields like provided. One fix can be that whatever the resource requires more number of resources. For example, fields requires more resources compared to registration and login, like pages, and your messaging require more number of resources. So probably you can add more resources to these tools and less resources to these tools. That way, what we call like cloud provides more better service provisioning and more efficient service provisioning with the help of microservices. So containers and microservices are very, very big, like change that brought in the cloud services adoption. Okay. And probably I should have taken some questions here, but let me quickly move on. And the next important change that has come in the recent times is adoption of serverless computers. Okay, and serverless doesn't mean that there are no servers. Okay, but the meaning is that servers are no longer involved. Okay, that's the meaning of it, right? It simply means that developers no longer have to think about servers and servers management, which cloud actually provides. Okay, so the servers management can also be leveraged. So in the olden days, these servers are actually built up by the cloud service providers and users. Now these are serverless in a sense that you can focus on designing the application rather than creating how to create the server, how to configure the server and all that. So the configuration, provisioning, and all these burdens now can also be leveraged to the cloud service provider, so that you can actually enjoy the beauty of cloud computing. Okay, there are several tools available for doing this. For example, Azure Functions, Amazon Lambda, Google Functions are a couple of examples of provisioning of serverless computing mechanisms. Okay, so I'll skip this as a in the interest of time, how this is actually done. But as I mentioned, there are a lot of benefits of this, where like you can have micro billing, okay, more scalability, no server management. These are all typical advantages. Yeah, yet another important innovation in the cloud environments is distributed cloud computing, where the cloud computing technologies are distributed in such a way that you can deploy these cloud services at the edge of the devices like mobile or IoT, what you call it as continuum of the cloud and the devices. That's where new kind of terminologies are evolved, like edge computing, fog computing, which were actually developments started from the in the olden days. We used to have the term like cloudlets or mobile cloud computing, which actually used to have the current day edge computing technologies for mobile specific implementations. And we have also have these days mobile edge computing, or similarly the IoT based edge computing, or fog computing exclusively in the interest of general word is fog computing, where you can adapt edge based architecture for mobile or IoT or whatever you call it. Okay, and this has created a new kind of research domain in the cloud implementation. That means cloud itself is a distributed computing environment, and think of something like distributing the cloud itself to multiple you can partition the cloud. You can think of it like that. Okay, so I'll skip the example, and just to give you a hint that a quick example is that cloud is having all the resources. Now what we have done is we have split the cloud into two components, bigger cloud and smaller cloud, where the cloud is very close to the devices, maybe your IoT devices or mobile device or whatever it is, and part of the job is done in your edge or fog computer, which is replica of your original cloud. Maybe I can show you this figure. So these are the small clouds, replicas of your original cloud, which are very close to your devices. That's how they are edge computers. Sometimes we call them as edge computers. Otherwise, very broad term is fog computers or fog nodes, which are essentially the what you call replicas of the cloud computing. So the benefit of having edge computers is to have low latency, because the processing is done locally, and they act like cache of your computer architecture, where the locality of reference acts it becomes an important tool here. And the major advantage of edge computing or fog computing is that it allows data explosion, where as I told you, data is growing like anything, and having a local computer can like process the data locally, and only meaningful data is actually transferred to the main cloud. So this is the beauty of your edge computing. So that way, the data explosion problem can be sorted out. So there are a lot of challenges with the edge computing, and new research like dimensions are evolving because of the edge computing and fog computing. And those who are interested in taking up research can think of edge and fog computing in the cloud to develop several algorithms to overcome these challenges.